Good afternoon, everybody. You are welcome to the August edition of NARC seminar series. And we invite you to this seminar where we invite speakers from around the world to give us a talk on current trends in numerical analysis research. This month's talk will be given by Dr. Samuel Essang, and his topic is integrating numerical analysis and machine learning for predictive modeling of complex engineering systems. I'll call on Ms. Roida to read the bio sketch of Dr. Samuel Essang.
Good afternoon, everyone. Dr. Samuel O. Essang is a mathematics lecturer in mathematics program, Department of Physical Science, Landmark University, Omu, Nigeria. His research interest lies in convex optimization, mathematical modeling, data science, and machine learning. His scholarly work applies mathematical and computational methods to optimization algorithm, neural network, artificial intelligence, predictive modeling, and interdisciplinary scientific problems. His current interests include integrating numerical analysis and machine learning to improve simulation, prediction, and decision support in engineering, energy, and earth-related systems.
Okay, thank you very much, Ms. Roida, for that bio sketch. I will now call on Dr. Samuel to share his screen and begin his presentation. Dr. Samuel, over to you, please.
All right, thank you very much. It is a great pleasure to be here. I must say a big thank you to Professor Julius Hige. I also want to say a big thank you to the team that have made this possible. I also want to say welcome, and we hope to have one of the best discussions, and I believe that so much will be gotten from this discussion that will lead to future and better discoveries. My name is Dr. Samuel Essang. I am a mathematics lecturer in a mathematics program, Landmark University, Omu, Kwara State. I would love to share my screen. I think I can go ahead and do that.
Yeah, please go ahead.
All right. So I would love to know when you have seen the screen. Please, can you confirm that the screen is clear?
Yeah, clear.
All right. So, thank you very much. All right. So, I'll be discussing integrating. Please, Prof.
Yeah.
My time schedule. Would I like to know my schedule? I work according to time.
40
minutes. All right. That is brilliant. So I'll be looking at integrating numerical analysis and machine learning for predictive modeling of complex engineering systems, integrating numerical analysis and machine learning for predictive modeling of complex engineering systems. So let's look at the roadmap. Clearly, we know that the central argument is that numerical analysis gives physical structure, and machine learning, on the other hand, gives speed after training. So a reliable engineering model should combine both carefully, then check predictions against physical evidence. So the combination that is done carefully of these two structures, structure of numerical analysis, which assures us of physical structure, and also machine learning that gives speed after training. And I always like to tell everybody when you are using your AI, using any of this LLM or large language model, that is a system or a structure that has been birthed, has been constructed by accurate large machine learning structure. So by a very large machine learning structure, we create what we call the artificial intelligence. So they are not really two worlds apart. So we'll be looking at the first part, which is the key definitions, general equations, the hybrid workflow. The second part, we'll be looking at the heat pipe system, the expansive soil widening, and the offshore monopiles. These are new and recent work in which I will encourage everyone who is in numerical analysis to engage in this work. I'll also be suggesting recent papers where you can use as a structure or your guideline in your analysis or research. The final part will also be talking about the validation metrics, the common errors, and also our research direction. Most of us already know this, but I will always start with this. Numerical analysis is the study of algorithms used to approximate mathematical models or problems that cannot be solved easily in closed form. So generally, if you have an integral of 0 to 1 of f of x dx, if you can integrate f of x dx algebraically and substitute your bounds 0 to 1, then you know you can do that algebraically and you don't need numerical analysis. But sometimes when you have an integral of x that is very complex in nature and that cannot be solved easily, we seek the help of numerical analysis for discretization and solution to that system. So numerical analysis is the study of algorithms used to approximate mathematical problems that cannot be solved easily in closed form. Now, many engineering systems are represented in differential forms and equations, boundary conditions, and material laws. So numerical analysis replaces the continuous problem with a finite computable approximation. And what we can see, so f of xt can be replaced with n u of xt with respect to lambda, which is a parameter. And also, g of xt can be replaced with the function bu of xt, which is the composite function of u of xt, x of t being points on the domain of omega, and we are considering the structure 0, t, closed structure 0 and t. I believe I'm talking to mathematicians, so we should understand these terms. U there is your known function, or what we call your known response field, such as temperature, displacement, or pressure. Lambda contains material, geometric, or operating parameters. But generally, when you see lambda, mostly we use it in representing parameters, where B here imposes a boundary or initial conditions. The B imposes a boundary or initial condition. So these are the system. This is the system we are talking about. If you've been doing a lot of work in numerical analysis and differential equation, partial differential equations, and a lot of systems and modelings, you will know that all you do is to reduce even optimization systems, optimization problems, is to reduce your system to 1 and 2. The boundary system in this case can sometimes be the constraints in an optimization problem, speaking to optimization experts. Now, machine learning, surrogate, and hybrid models. I would like to inform you that most cases where we discuss machine learning, we talk about hybrid model. But hybrid model means combination of 2 or 3 or 4 models. I've written a particular paper where I combine about 5 activation functions to give a stronger hybrid model for machine learning of a particular model. So machine learning surrogates is a fast approximation trained to reproduce selected outputs of a slower numerical model or experiment. So this is a model in equation 3 and 4, where y cap, of course, represents the estimate of m theta with respect to x. That x is a list of your parameters. So whatever parameters you have in mind, you construct a list of that parameter. You construct a list of that parameter. That's what we call x. So x is not just a single variable. It is a vector in this case. And we also have a model. And the model is a popular machine learning model, training model, L data with respect to theta, where you can see the y cap, which is a parameter, difference with yi, which is your respective data for y. You square them and find the sum and divide by your sample size. Sample size is always extremely large, and these parameters are actually large. Sometimes they range in thousands, hundreds of thousands. So it is not something that you can do by hand. It's something that can be run, not just by any software, but can be trained with the help of machine learning surrogates, an hybrid model. An hybrid predictive modeling has to do with a hybrid model that uses physics-based simulation to structure the problem and machine learning to accelerate prediction and to classify behavior or estimate parameters. So I want us to get this point, that the hybrid model, it uses physics-based simulation to structure the problem and machine learning to accelerate the prediction and to classify behavior or to estimate the parameters, like I have said earlier on. These are three anchor studies that we'll talk about, and that has to do with Zhang et al. In 2026. It's a new work, the system has to do with high temperatures, heat pipes. Yang et al. Is also working on the expansive soil road widening, and we have what we call Ph.D. et al. Ph.D. et al. They are working on offshore wind-turbine and monopile foundation. The hybrid method that is used for the system is the methodological review covering experiment. That is simplified numerical analysis, CFD, and machine learning. We have what we call the abacus, not the other abacus used for counting. This is called abacus. It has to do with hydro-mechanical finite systems or elements combined with the machine learning swelling coefficient model. We also have the abacus finite element outputs that is used to train ANN, that's artificial neural network, and random forest displacement predictors. So these are new research that is ongoing, in which I will encourage us, for those who have research interest in these areas, to take advantage of this. All right. So the common thread, all three papers are numerical modeling as a physics-based and machine learning as an acceleration fitting or prediction tool. I want to encourage you, the work is new. For any of us who want to do something new that combines numerical analysis and machine learning, these are three papers using numerical modeling as physical base and machine learning as an acceleration, fitting, or prediction tool. Now, why hybrid predictive modeling? Why? Why hybrid predictive modeling? First reason is that engineering simulation can be accurate but expensive when repeated across many design cases. So we want to see how we can always maximize profits. We want to see how we can maximize time, and also see how we can maximize effort. And one of the ways to do this is to apply predictive modeling. And machine learning can be fast. It can be fast, but unreliable if it's detached from physical assumption and validation. This is where we have to be careful. And that is why there's so many warnings on AI use. AI use must always have physical assumptions and validations. So we must always check. If you are using any AI tool, they will always tell you to check that AI do make errors. But always check physically to ensure that the rate of error is minimized. We know centrally the aim of numerical analysis is to minimize error as much as possible. So machine learning can be fast but unreliable if it is detached from physical assumption and validation. Hybrid modeling uses credible numerical simulation as structured data generators and experiments. Field data or published benchmarks remain necessary for checking realism. This is very, very important. I must state this, and we must take note of this. No, so what's the main research question? How can finite element that we know in numerical analysis, CFD, or coupled numerical models be integrated with machine learning without losing physical meaning? I needed to write this without losing physical meaning. What's the practical answer? Use physics first, use data second, and validation throughout. This is the key word every modelist, every mathematician, every numerical analyst should have in mind, that first we must entertain physics first, having the strength and background of mathematics. Data should be considered second, and validation should be done throughout as the research is ongoing. So finite element approximation, we'll know this. I won't take my time on this. We know that in the finite element model, the unknown field is approximated by the shape function, which we see, UH of xt, where n are basis function, ui are nodal unknowns for a static structural problem. The discrete equilibrium equation can be written as k of lambda u equals to f, where k is the stiffness matrix, u is the nodal response vector, and f is the load vector. So what is the presentation point? The finite element output become useful machine learning data only when the model assumption, the mesh, the boundary condition, and the parameter range are credible. So must take note that the machine learning data we are dealing with must have its model assumption, the mesh, the boundary conditions, and parameter ranges are very, very credible. This is one of the reasons any work we are doing now that has to link with machine learning has to be checked over and over again. There has to be a high level of credibility since we are dealing with numerical analysis and engineering as a whole. Now, when a governing equation is known, whenever a governing equation is known, I'm talking about the physics-informed learning concept here. When a governing equation is known, the learning objective can include both data error and physics residual error. So we must know this. And this is the one equation we can have handy. Equation that has to do with L total with respect to theta, the L data, and also the L physics multiplied with alpha. Alpha here represents the learning rate. Sorry, I may not have written out some definition of some terms here, but as I speak, I'll be naming them. So alpha there, which is the coefficient of L physics with respect to theta, is actually called the learning rate. And our aim is also to work on the learning rate. We keep working on the learning rate to ensure that we have the level of accuracy and limitation and limit in our level of error. So we have L physics as the formula you see in equation 8. So from the model in equation 8, we substitute in 7, we combine it with the L data, which is the formula or model we have mentioned earlier, and that gives us L total with respect to theta. So the data term keeps the model close to observation. The data term keeps the model close to observation. And we can, these experiments also depending on even the simulation outputs. So physics term, penalizes violation of governing laws, like governing laws, the governing laws of heat, governing laws of temperature, governing laws of force, Newton governing laws, gravitational laws, and all that. There are really many, and the new ones which they're talking about in nanophysics and all that. So it penalizes violation of governing laws such as heat transfer, mechanics, or flow equation. And now, this is a hybrid workflow. First, we'll consider the physics and assumptions. Consider the physics and assumptions. Secondly, we'll consider the FEM, we'll consider the CFD, and also our couple solver. This is terms that numerical analysis are used to. So we don't have a problem with those terms. Then we also consider validated response data. This has to do with now the data we've gotten. That has to do with the data that we have gotten. Then we also discuss the machine learning surrogate training. And finally, the restricted prediction domain. So the physics and assumptions, finite-element method, CFD, or couple solver, the validated response data, the ML surrogate training, and finally the restricted prediction domain. So the stage physics has to do with state equations and assumption. I had to break this down so that for some people who are younger students will be carried along aside what we are doing. So I had to take my time to break down some things. So in physics, we state our equations and our assumptions, or the Newtons and the Einstein and all those equations. And then the quality check we do, we avoid black box modeling without physical basis. If it's simulation, we run FEM, and which is the finite element method. We also run the CFD. We run the CFD, and when we run the CFD, we do that with our coupled analysis. We check mesh, check boundaries, and parameter range. Check the mesh, check the boundaries, and the parameter range. And the learning, this is where we come to machine learning now. We train the artificial neural network. Please, in case somebody asks, SCFD simply means computational fluid dynamics. Please, computational fluid dynamics. So learning, we train ANN, we train the random forest, train the GRU, and other models. There are so many of them, so many of them. And we report, train, we validate, and also test performance as our quality check. Then what do we use it for? We predict new but similar cases. But here we do not extrapolate beyond the validated domain. Of course, that would be a risk. Anything you are doing will be within your domain. So you do not extrapolate beyond the validated domain. Even within your own domain, there's still level of check rather than you going outside your validated domain. So that must be put into consideration. All right, so case study 1, that has to do with high temperatures and heat pipes. The paper that has to do with Zhang et al. That's reviewed 4 methodological families of high temperatures heat pipes, namely simplified numerical analysis, CFD, and machine learning. This is a work that is brand new. It's a numerical model that simplifies startup and steady operation. The CFD visualizes the two-phase flow and temperature field. Finally, machine learning supports performance, prediction, parameter inversion, and rapid modeling. You can see the model for the thermal resistance, where TE is the evaporator temperature, TC is the condenser temperature, and Q is the heat transfer rate. Then for these heat pipe methods and reported machine learning examples, you can see that for the experiment, direct evidence of startup and steady performance. Numerical method is fast approximation of macro scale thermal behavior. And the CFD here, and CFD, that's the computational fluid dynamics here. I have the detailed visualization of temperature, pressure, and flow fields. And the machine learning here helps us for rapid prediction from validated data. So we can see what our the CNN and the MAE value is scaled at MAE per 10, and that is good enough. If MAE per 10 is very good because for some jobs, that have been done before, you have MAE per 15, MAE per 12. So this is MAE per 10, which is a good result. MAE per 10 is a very good result. And the reported MAE here was 0.41 E. So this is a very good work, which we can also indulge in research that can give us probably a lower MAE. All right. So what is the take-home point? The paper presents integrated multi-methodology as likely direction for intelligent multi-scale heat pipe design. So the paper presents integrated multi-methodology as the likely direction for intelligent multi-scale heat pipe design. This is a recent one. So we move to case 2 that has to do with expansive soil road widening. The expansive soil road widening. So here, expansive soil swells when water content increases and shrinks when water content decreases. This behavior can create long-term settlement and differential deformation in road widening projects. So we can see the model that represents this phenomenon. E total equals to E load plus E swell. E swell is something as this parameter beta with the change in S. The change in S has to do with change in saturation, and beta is the swelling coefficient. So the numerical part is the abacus hydromechanical analysis with user subroutine. The abacus hydromechanical analysis with user subroutine. This is one area I will also, it's new, also advise us to indulge in if we want to do some fresh research in this area. Now, we also have the machine learning part, which is the polynomial. Of course, we know what the polynomial is. The ANN has to do with artificial neural network, GRU models, where they were compared for swelling coefficient fitting. Okay, so please, the abacus, please take note, it's a powerful software, a software for finite element analysis, FEA, and computer-aided engineering. Some of us should be aware. I'm sure some of us have been using it for our experiments. It's a very powerful software, and that is used for finite element analysis and also used for computer-aided engineering, that is CAE. Okay, now we can see the expansive soil result, the reported values. You can see for the three cases considered, we have the polynomial, which is reading 0.82. We have the artificial neural network, 0.97. And we have the GRU, which is reading 0.98. So it is not a case where we depend on one of the model alone. We have to try, started from the polynomial. We know that early then in the 80s and in the 90s, curve fittings, I'm sure we all know about curve fittings, and that was the trend then with the use of Taylor series, power series, and all that. So our main aim, our main work then was, on polynomials, but the era came where we started talking about artificial neural network. I think some people will be thinking that artificial neural network now is the newest. No, we now have what we call even the GRU, which has to do with gated recurrent unit. What we call the gated, that's what GRU means. It means the gated recurrent unit. It is actually a very highly effective gated mechanism in recurrent neural networks, RNN, the beginning of recurrent neural network. It was introduced in 2014 by Kyung-Yoon Cho et al. So it is, designed to solve vanishing gradient problems that have plagued standard RNN. So it's a very interesting area. It's also used in long short term memory, that's LSTM network, as they achieve similar performance but they require fewer parameters and tensor operations. So it's a beautiful, it's a very interesting mechanism that is used in neural networks, recurrent neural network. All right, so here you say that the GRU fit was strongest among the tested models. So among the tested model, you see, we can boldly say that this was the best for now, when expansive soil subgrade deformation was included. Maximum pavement settlement increased from 2.5 cm to 12.3 cm in the reported comparison by Yang et al. In 2026. Now, the offshore, the case study 3 is the offshore wind turbine monopile. The offshore wind turbine monopile. This is done by Ph.D. and friends, Ph.D. and co-authors in 2026. They also use the Abacus simulation to study monopile response with stone column ground improvement. The finite-element output were then used to train ANN and also the random forest model. So we have the mud line displacement reduction. And you see, of course, the first giving us 0.8 meters, the second 1.0 meters, and we have 1.2 meters. You can see the level of reduction in the mud line displacement. Of course, what is the reported engineering result? At the mud line, displacement reduction was reported at 11.2%, 21.4%, and 24.4%. For increasing stone column diameter, the maximum tip reduction was about 23.5%, when DSE was equal to 1.0 meters. So you can see that the machine learning models used with the ANN with Bayesian optimization and random forest with grid search cross validation. All right, so here we can see the comparison, can take out the comparison of ANN and RF. And here there's validation for R squared. These are validation for R squared. And we also have the reported validation errors. We see that ANN is having the less error here. ANN using MAP is having 1.56. The RMSE is having 13.47, and RF MAP is having 5.25. So what this means is that both models perform strongly in the study. Both models. They perform very well in the study, but the reported ANN metrics were better for displacement prediction task. And I need to state this. I've reviewed several papers where authors will write a paper and only use just one machine learning model. This is not acceptable. And some of them will get so angry and say, oh, I use this model, I have this accuracy, I have that accuracy, and all that and all that. But I always advise, when you're dealing with machine learning models, you always try at least 2 models. You should be able to say, okay, this model and this model is used, but this one gives me better validation error, and this one gives me the best validation error, the best in quotes anyway, because whatever you say best today will be better tomorrow, because there will be another validation model that is better. So using the machine learning model is not always advised. You want to use 2, you want to use 3, you want to use 4, they are good. Of course, it is the best with the least error that will be considered. So of course, we are used to this. We are used to these formulas. Whenever you are dealing with machine learning, you always use this model to validate your result. So these are validation metrics that should be reported. So anytime you do after your numerical analysis and you have applied them in the engineering complex system, you must do your validation metrics. And of course, the validation metrics, we have the R squared that is popularly used. We have the RMSE. The RMSE is root mean square error. It's called the root mean square error. The root mean square error. Of course, the root mean square is a standard statistical metric used to measure the average magnitude of the error between the predicted value and the actual observed values. So it is a standard statistical metric used to measure the average magnitude of the error between the predicted value and the actual observed value. Of course, it should be as small as possible, so as small as possible, So in machine learning generally, or maybe regression analysis, because this is where it started. Originally, it was used in machine learning analysis. So in machine learning, regression analysis and numerical modeling, it actually serves as a primary loss function. I'm sure we are used to that term. It serves as a primary loss function for evaluating model accuracy. So it serves as a primary loss function for evaluating model accuracy. And we should take note that because RMSE squares, I cannot square the errors, before averaging them. That is, when you look mathematical view at it, you see that it squares the errors before averaging them. So it is heavily penalized, or heavily penalizes large deviations, and it makes it highly sensitive to outliers, and also compares it to other metrics. So we must take note of all this. We must take note of all this. All right. So because of time, I need to move faster. So high R squared is not enough. High R squared is not enough. A serious report should include absolute error, relative error, independent testing, and physical range of the training data. So a serious report should actually include absolute error, relative error, the independent testing, and the physical range of the training data. In case somebody wants to know what MEP is, it's actually a highly popular statistical metric used in measure to for prediction of accuracy or forecasting models, unlike metrics like the one I just talked about, it's RMSE and others. Okay. All right. So I move on. So how to avoid misleading hybrid models? How do we avoid misleading hybrid models? This is very, very important. The common failure point is that we have weak or unverified numerical models, training data concentrated in a narrow region, no independent test sets, surrogate used outside its training domain, and reporting R squared without error size or physical validation. And minimum safeguards. How do we safeguard these? Document governing equations and assumptions. Validate against laboratory, field, or literature data. This is very, very key. Very, very important. We always learn to validate against laboratory, field, or literature data. Use train, validation, and test separation. You need to use train, validation, and test separation. You need to plot predicted versus observed responses. This is very important, especially when we are delivering a paper. You have to plot predicted versus observed responses. And you need to add sensitivity and uncertainty checks. So always add the sensitivity and the uncertainty checks. So advice I wrote here, I said, explain the machine learning. Explain that machine learning is not replacing numerical analysis here. Please. Machine learning is not replacing numerical analysis here. It is reducing repeated computation after the physics-based model has been built and checked. This is plain advice for tomorrow. Before somebody will point his hand at me and say, oh, you say you should not use numerical analysis, you should use machine learning. Please, that is not what we are saying. Okay, machine learning is not replacing numerical analysis, and it cannot. Very firm. It cannot replace numerical analysis. It is only reducing repeated computation. It's only reducing the number of costs or stress that you would have gone through, as after the physics-based model has been built and checked. This is very important. So research direction for the seminar group. I've been saying this, at the course of this delivery, but I need to emphasize it here. We need to build benchmark problems where FEN and CFD outputs are verified against experimental or field data. 2, compare classical regression random forest, artificial neural network, GRU, and physics-informed learning on the same data sets. 3, report accuracy, speed up, uncertainty, and physical consistency together. 4, develop reusable open data sets for African engineering system, especially soil, energy, infrastructure, and healthy related transport models. Now, what is the proposed working theme? Physics-guided numerical simulation and machine learning surrogate for reliable engineering prediction. So this is what I'm giving us as a sketch, what I'm giving us as a framework. You can work around this to build your topic, physics-guided numerical simulation and machine learning surrogate for reliable engineering prediction. So conclusion, my conclusion is that numerical analysis remains the physical foundation for modeling complex engineering systems. And another thing is that the machine learning is most useful. Yes, machine learning as for now, machine learning is most useful as a validated surrogate, not as an uncontrolled replacement for physics. The 2026 studies that I have brought to you shows credible hybrid used in pipe pipes, expansive soil, road widening, and offshore wind turbine monopile foundations. And reliable hybrid modeling requires clear equations, please. Verified data, transparent error matrix, and domain restriction. These key things are very important. By 1, clear equations, verified data, transparent error matrix, and domain restriction. And future work should move toward physics-informed, uncertainty-aware, and experimentally validated predictive model. My final message, good prediction is not only about numerical accuracy. It must be traceable, physically meaningful, and useful for engineering decision. A good decision is not only about numerical accuracy, it must be traceable, physically meaningful, and useful for engineering decisions. And these are the references that will also help you. I want to say a thank you to everyone, and we are open to questions and discussion.
Thank you very much, Dr. Samuel Essang. I'm really very grateful for your, very, well taken lectures, because this is like a lecture in class, and you try to, go down to the basics and the foundation for even people that cannot really understand the hybrid models, as in using, coupling, adapting, neural networks and machine learning to numerical analysis. And just like you rightly said, it is not a replacement for what they call for numerical analysis methods. So I will now welcome questions. If you have questions, just signify by raising up your hands, and I will select you. Questions? Do we have any question for Dr. Essang? Okay, I can see two hands raised up. Okay, let's start from Dr. Daniel. Can you go ahead with your question? Unmute and go ahead with your question.
Yeah, hello, good afternoon. Can you hear me?
Yes, yeah, we
Very
are
well.
audible. Yeah.
All right, thank you very much, sir. So I want to start by saying I want to appreciate Dr. Samuel for this lecture. Sincerely, for me, it's an eye opener, and it's, I would say, one of the wonderful lectures I've listened to in recent time. So thank you very much, sir. My question now is, you actually talked about how to the numerical simulation and ML like surrogates. So I want to ask, is it that the model, like the simulation was done first, then after it was done, the data gotten from the model is now what you now use to train your machine learning? Or I really don't get that part, because I'm new to the area of machine learning, but I have a bit knowledge in the numerical analysis space a bit. Thank you, sir.
Thank you very much for that question. That is a beautiful question.
And also again, sir, I'm sorry, sir. I don't know if I'm permitted to ask another one.
Yes, you
Sure.
you can ask, please.
Okay, so I want to kind of make like a bit of lobby to know if I could personally reach out to you after this meeting. And I just stumbled on the meeting invite from one of the WhatsApp group, but I'm not like, and I got interested in the topic and the whole stuff. So I will be glad to also join the series monthly
Okay.
and also
Okay.
reach out. Thank you, sir.
So I'll put a you can Dr. Exam you put his his email address on the chat box now, and I will also put a number on the what they call it on the chat box for you to reach out to the person so that we can include you in the list of we have a list of emails that we send every month for our meetings.
All right, sir.
Okay, so Dr. Essang, you can put your email and answer his questions.
All right. Thank you very much, Doc. Whenever we are dealing with machine learning, there are two things involved, and it has to do with training and testing. Training and testing. Okay, just have that in mind. In machine learning, two data involved. Another word, you remember in secondary school, we used to do what we call percentage error. I don't know whether you remember something like that, percentage error, where you will
Yes, sir.
a tailor measured this, and the actual measurement is this. What is the percentage error? You remember that? That scenario is not different from what machine learning is doing. All right. So there is this data that is always obtained, and there is this data that is always simulated. So there are data from simulation, there are data that are observed, some observed from the field, and some observed from simulation. You get me? So there are other data that is difficult to obtain that sometimes we do by simulation, or sometimes we actually compare the simulated data with the already available data. So it always has to do with those two data. Okay, so we have to do with the training and the testing. So when building a model, a single master data set is divided into two separate sets. Are you following me now? To ensure that the algorithm actually learns, what do they call it? Pattern. That's what they use. Pattern, rather than simplifying, memorizing, or memorizing the answers. Okay. So training. The training has to do with the largest portion of the data set. Okay. The training has to do with the largest portion of the data set, typically 70% to 80%. So the algorithm analyzes the data repeatedly, adjusting the internal parameters. I don't know the term they use, but internal parameters to learn mathematical relationship between the input and the desired output. And on the other hand, we now have testing. In testing, the other one was how many percent did I call it? I think 70%. So the remaining now will be 30%. So the remaining 30% is what we call the testing data. So the testing data is what we call the unseen proportion. That is the unseen in quotes, unseen proportion. So once training is complete, the model makes prediction on this set. Okay, the model actually makes prediction on this particular set, which is the testing data, because the model has never encountered this specific data before. So it acts as a final exam to measure how accurately the model will perform in real world. So anytime you're dealing with data, you always divide it. 70, you use it to create the model. The remaining, you use it to check if the model is working accurately.
Okay.
I don't know if my question. We also have another one.
I think you answered the question, Dr. Samuel.
Sorry, can I just add a little to the answer?
Okay, carry on.
Yes, please come on.
Yeah, my name is Dr. Chinedu, speaking from Port Harcourt. Okay, so the question he asked, the answer is actually yes. So what the presenter is saying is that if you have like the Navier-Stokes equation that
Okay.
predicts the velocity and pressure of a fluid
Or
flow.
flow. Yes, sir.
Yes. And then now, if you have a finite element solver that solves Navier-Stokes equation, it is very expensive to run every time.
Good.
So what he is talking in this presentation is that you can use that your Navier-Stokes solver to generate a lot of data for your velocity and pressure, and then use that data now as your training and testing and all of that, instead of going to get experimental data. And then that's what you now use, and then to produce your surrogate model, so that whenever you want to make that prediction, instead of coming back to the CFD Navier-Stokes solver, you use the surrogate, which you have obtained from machine learning. Present, I don't know whether I answered it. I suppose
Excellent. That is perfect.
Wow,
thank you very much, sir. Thank you very much, sir.
Okay,
thank you.
Dr.
The Navier-Stokes equation you used to explain makes me understand better. Thank you very much, sir.
Dr. Ekebe, your question, please.
First of all, I'm not a doctor. I'm just an MSc student under Dr. Lige. All right. So my question is if one is to carry out a prediction of device failure using numerical methods, can I combine numerical methods and machine learning, or will I say numerical methods on machine learning over prediction of network devices? Because you from your presentation, I learned that machine learning should come last, data validation should come first, something like that. So ever since I tried doing this a while ago during my internship. I ran the prediction model. I used a random forest model to predict device failure. At convergence, I actually stored the model. I want to find out now numerical analysis can be run on machine learning. I want to see, am I to combine both of them, or numerical analysis comes first before machine learning? That's my question. I don't know.
Yes, to be very sincere, numerical analysis and physics-informed model comes first. Those are the foundations, those are the backgrounds. Machine learning is just for validation and speed. Validation, checks, and speed. But the structure for everything we are discussing now, first is the physics-informed model. Our equations, like the Navier-Stokes. Thank you for mentioning Navier-Stokes equation. Like the Navier-Stokes, these are physics, these are, our models, equations that already exist. Are you understanding me? So the numerical analysis here brings in iteration in a case whereby you cannot solve algebraically, and your answers cannot be gotten in closed form. That is where numerical analysis come in. Now, how can I now do this faster? How can you now do this with checks and accuracy? That is where machine learning comes in.
Okay.
So, Mr. Efe, you know that before you can use a machine learning model, you need data.
Yeah,
right?
I need data. Yes, sir.
But this data now is now going to be obtained from the numerical analysis, using numerical analysis to solve the problem first. You see that?
Okay.
So numerical analysis is first. The machine learning is not actually replacing numerical analysis. So it's not going to replace it.
It can't.
What is just doing is it's going to first, your numerical analysis will give you a set of data, maybe I'm going from 0 to 10 minutes, for example. You want to know what's happening between 0 to 10 minutes. Numerical analysis first gives you that. But to achieve that, numerical analysis struggles a lot. Maybe the computation is very expensive to do that. You get that?
Yes.
So that thing it has given you for running for the first time, right, is that it has given you the results from 0 to 10. But the problem is, if you're coming back to run that thing with a different parameter, you have to change, you have to go back to the code again from the beginning. So what you can do is, that first one it has given you is like a data which machine learning can learn maybe from 0 to 8 seconds. So the machine learning can learn from 0 to 7 seconds to know how that thing is behaving and get you a model to show you the behavior of that thing between 0 to 8 seconds and give you a model that can stand.
Okay.
So from there, your machine learning now helps
From there.
you to now generate results, and you can validate to the remaining 30% to check if your machine learning model is good or not. You get that? But so by the time you are sure that you have a good model, then you can just use that to be doing anything you want to do again.
Okay. I understand quite 100%.
So Dr. Samuel, so I hope what I'm saying is what it means.
You are doing well, sir.
Thank you so much.
Right. Okay, so Mr. Chris.
I understand, sir, perfectly.
Okay.
Mr. Chris, please, your question. Mr. Chris, your question.
Okay, good afternoon, Dr.
Yes, good afternoon.
Dr. Samuel and Professor Ehide and Dr. Chinedu, Professor Chinedu. I really want to appreciate you for Dr. Ehide for this platform. It has been very helpful. And today is like one of the best days I've had because it's actually connected to what I'm presently doing. So I'm currently a PhD student in the lab. My field of area of interest is fluid dynamics. So, and I'm actually working on mathematical modeling and the data-driven prediction of a reactive magnetodynamical fluid using finite-element method.
Wow.
So I think it's really in line with what the doctor just explained. So my question is because where I am now, I'm looking at because I'm really pretty new, sorry, in this field. Actually, the machine learning, I'm actually at part I'm new, I'm a beginner. So I thought to implement it in my work. So I'm handling the physics and the numerical method, the finite-element method. But my challenge now is how to use machine learning to validate my work. So I don't know how to be able to be of help to me. Thank you very much.
Mr. Chris, I think where you are is very noisy. We couldn't hear your question. I don't know if other people heard your question, but I couldn't hear.
We didn't hear his comment. We didn't hear him.
Can you go somewhere that is very silent? Yes, we can hear you now. Please speak louder.
Okay. I said that I'm actually a student.
Yes, your question.
Okay, yeah, my question is, I'm developing a model. It's a mathematical modeling of data-driven prediction of a reactive MHD castle nanofluid squeezing flow through that's it for Heimer porous media using finite elements. So the combo, I'm using both the finite elements and also the machine learning. So now I have the physics already. I'm handling the physics. The numerical method, which is the finite element, but the challenge I'm having now is the machine learning implementation. So I'm new, so I want to know how to, because I understand the background on how to, because initially I was thinking of using MATLAB to generate synthetic data. Then I'll now use the data I'll get from MATLAB to train the AI bots. I don't know. I'm just like, I don't know how to go about it. Thank you very much.
Is Dr. Essang, okay. Maybe Dr. Essang, if Dr. Essang could get a question, because I think he's mute now, I don't know. But if I understand you well, I think you can start with some machine learning textbooks, I think, to be able to implement that. Dr. Essang, are you there? I think we lost Dr. Essang.
Can I say something?
Yes, please.
I'm with you, I'm here.
Okay.
I am with you, I'm here.
Okay, so I don't know if you got the last question.
Yes, I got his question. Sorry, I forgot I muted.
So could you just recommend like a textbook for him? So if someone wants to start learning machine learning, could you recommend like a textbook for him?
So many. Maybe just email me and drop my mail here. I can.
Yeah, his email is there.
Yes, I've dropped my email so I can forward some good text for you that will really help you, especially machine learning for physics and informed modeling.
So, Mr. Chris, check the the chat box for his.
But to answer his question, I want to make you understand something, and this is what a lot. I always do this to my students for them to be clear that how do I put it now? A machine learning model is actually a function too, but it is a parameterized function. It is a parameterized function. I always let students know that it is also a function with respect to what? X, where that X there is your list. So I don't know how many things you have in your list. From whatever the experiment you are doing, you will always have a list. No. That list actually form your vector. Okay, when you get your vector, so that parameterized function, which is the machine learning model, is designed to approximate an unknown target function. Of course, if you are dealing with any differential equation, you are dealing with what we call an unknown function or unknown target function or distribution. Can be a function or can also be a distribution. So the aim is, I want to be clear about this. So we see the mathematics in machine learning. The aim is, it does this by optimizing its internal parameters over a given data set. So you are optimizing the internal parameters. How are you doing it? By a given or available data set. Of course, the model, it learns to map input. Sorry, I'm talking like a mathematician. It learns to map input to desired output while minimizing a predefined loss function. So that's the key thing you must have in mind, that the aim of this machine learning function is to predefine loss function. In other words, reduce error as much as possible. Reduce error as much as check and also reduce error as much as possible.
Okay, Mr. Is it Dr. Daniel or Daniel Osifua?
Yes, it's Mr. Daniel, not Dr. Daniel. Thank you very
Okay.
much.
You want to ask another question again?
Yes, something just came up. Like, I want to
Okay.
just get a clarification. I know there are diver numerical like CFD like software, but during this thing, he mentioned Abacus Sarah. So I want to ask, what's the role of because I, I I know some are open source and some are not. But what's the role of the like the CFD software in achieving accuracy in this type of numerical simulation and ML or like surrogate kind of like research? I don't know if you get my question, sir.
I think I get your question.
Okay, let me go to let me be like specific now. Say for example, I'm using console multiphysics. The way it brings out is data and results is different from the way, let's say, OpenFOAM will do that or MATLAB. So I want to ask, what's the role of the diversity in software, kind of? Thank you, sir.
On a rough note, let me say speed. On a rough note, let me say speed. You understand? But we have Abacus. I don't know if you have used Abacus before. We have
No, I
Abacus
have not, sir.
standard. Okay, it's a good software. We have Abacus standard. We also have Abacus explicit. So, of course, Abacus explicit is used in an implicit integration scheme. So if your integration scheme, you have an implicit function, that's what I mean. So for implicit integration scheme, you use the Abacus standard. Then I think for the Abacus explicit, use it for explicit integral or integration scheme also. Okay. So it depends. I don't want to go deep into that, but I know that for this implicit integration scheme, if you have a function or model that is static, low speed dynamic, and I've forgotten this other one, highly linear events. I hope I'm not speaking big terms. This highly
No,
linear
I think
event,
Oh, you are
I
not,
low,
think
sir.
okay, all this low speed dynamic, all this static, you use Abacus. You also have this highly non-linear transient. You have this other one, I don't know,
Dr.
dynamic
Samuel,
event.
I think he can reach out to you maybe later. Maybe you can just explain some things to him.
Okay.
Yeah.
So, but those abacus, like I said, roughly it is speed. It helps in the speed. It's for typical applications. It helps in the speed. they are just solvers. They are just unified solvers. We have what we call abacus CAE. That CAE means complete abacus environment, which are very,
Is
very
Professor Chinedu still here? Well, Chinedu, are you still
Yes,
here?
I'm still here. Yeah.
Okay.
Yes,
Now let me ask
that.
you, Professor Chinedu, maybe you can contribute to this question that he asked. Maybe I should ask it in another way. Suppose I use an Euler scheme of, Euler is just on that one,
Yes.
to solve maybe the resulting differential equation from the Navier-Stokes equation.
Yes.
Right? And I solve that, and I use that to generate my data, to generate my data set for my first computation. And somebody else uses the RK4 as the solver of the differential equation arising from the Navier-Stokes equation, after discretization and everything, right? What is the effect of this order on the machine learning result, on the final machine learning results? Can the machine learning lead to order reduction, or the order of the methods are sustained?
Okay. So the point is that in the first place, you use a high order method to solve your problem. So that means you have a better accuracy.
Yeah.
So the implication is, imagine that you're not even using a model to generate your data, because that is the whole thing we are discussing here, is the idea where you're using a mathematical model to generate a data, and that's where the numerical analysis is playing the role here by solving that model. So imagine you're not using a model to generate data. So the background.
So yes,
Okay,
I've mute the person.
Okay. So if you're not using that to generate, so let's say you get your data from the field, and then so the first order and the fourth order you're mentioning, it's just like you're having a better accurate data and a poor data. Good. So the high order method is giving you like a more accurate data. Why? Because it's more accurate to the model you're solving. Yeah. Why the lower order method is giving you a poor accurate data. So in general, the point there, which is why he's saying you have to validate the model. So the idea is that you want to get a model that actually represents the physics and the method that actually solve the problem accurately, so that the data you have from the model will actually represent reality. Because if you have the correct data for your machine learning analysis, then you will have your machine learning surrogate that you get at the end of the day will also make better prediction. Yeah. So that is the whole idea. So in general, so the point there is that it is advisable to use the best method as much as you can afford that's available to you.
Yes.
Thank you.
You're right. Yeah.
Thank you very much. Prof, let me also add something. From the mathematical aspect, another thing we really need to know is that the reason why we involved some of these numerical schemes, and we involve some of this software, and we involve machine learning tools, is because of the non-linearity of the differential equation we are dealing with. If all our differential equations were linear, we don't need some of these skills. Some good polynomial validation can sort that out.
Right.
Yes. Most of the Navier-Stokes is a non-linear PD, is a non-linear partial differential equation. One of the reasons that has pushed us to these extremes, or to this invention of these machine learning models, of these numerical schemes, higher standard numerical scheme, and even the softwares, is the non-linearity, handling the non-linearity, whether material or geometric or boundary non-linearity of equation. So we must always we don't just see any model, then we rush into these tools. We must also know that what is driving us is mostly the non-linearity of our models. For linear models, they can be treated easily with even older schemes.
Thank you very much. Okay, so at this stage, I don't know. Let me see if there's one of my. Okay, is Professor Olakule here with us? I don't know if he's here.
Yes, I'm here. I'm
Prof,
with you.
Could you just say a word before we leave?
The only thing I can say is to thank my prof. You really made it simple. And I believe most of our students must have gained immensely from your contribution today. I hope, Dr. Ige,
Yes,
you
sir.
will call him back. We still
Okay,
have
sir.
more to learn from him.
Okay, sir.
Thank you so much. We are grateful.
Thank you, Professor. Okay, so at this stage, I will use this opportunity to thank Professor Aishimoju, I think is here. I'll thank Professor Nwagwe, my very good friend. And Professor Nwagwe, I still have something to collect from you. The third fund something.
I hail you. I hail you.
I saw the third fund something. I can't collect my own. Okay. and our presenter for today, Dr. Samuel Essang. I am very grateful for your, for your very, very, well put lectures. In fact, you've simplified everything, even as much as, you try. I saw that you try to avoid a lot of the mathematical foundation of the machine learning itself. I saw that it's quite omitted, but, I'm sure that's why Prof is saying that we call you back. Maybe in your next lectures, you now open up all these loss functions and the, automatic differentiation and those things. You're going to now do all those things, the training rates, the Adam, what they call it, optimization technique and those things. You're going to now open those things for us to learn these things very well. I want to say a very big thank you. And to all the people that came for this, what they call it, this talk. And I know Miss Festa is here. I don't know if she's still here. Yes, I want to thank her too, because she has been the backbone of, doing some dirty jobs, sending emails to our participants who are on our list. I want to say thank you to everybody, and I say bye-bye till next. Yes, next, what they call it? Next, in September, next month, will be, the lecturer for next month will be Professor Patrick Farrell, who is the winner of the Gemond Dalquist Prize for 2026 from the University of Oxford. So we'll be having him in September, and I hope we'll all be around. Please tell your colleagues and your students. In fact, students I even want to be here. For me, if I even want master students, PhD students, because we need to change the narrative of numerical analysis in Nigeria. That's the aim of this. So we want students that are just coming up to begin to see contemporary research areas, because I can tell if I ask an average Nigerian what he's doing in the masters, I can guess what he's doing already. I know what we do here. But my aim is just to find, new areas of what is trending, in the world, and I want students to begin to look at these areas. And maybe in November, I don't know if Professor Nwagwe will be ready to give us something. I don't know. He's been running away from me for a very long time, but I hope that we will be able to see. So see you next time, guys.
Thank you very much.
Yeah,
Thank you.
Yeah, bye-bye.
Thank you very much, man. Bye.
All right, thank you very much.